AP Calculus BC, Unit 8, Day 5 office hours. There's no lesson. This is just some more practice, what we were doing before. So there's a few problems from page 502, 1 through 4 all. It's a quick quiz. So they are multiple choice questions. We'll just do them. It says, number 1, which of the following is the sum of the series? So I'm going to write it down. N equals 0 to infinity pi to the n for e to the 2n. I want to know the sum. Now here's the deal. Is it a geometric series? Because that's the only one we really know how to find the sum of. So, you can start writing the terms out. I don't think that's necessary, but you could if you want. I think I see that it is an r value to an n. So, I just look at this. I say, I think r is pi over e squared. You plug 0 in, you get 1. So the a value is 1. You could start plugging these in. You get 1 plus pi over e squared plus pi over e to the 4th. Same pattern. So is the absolute value of r, you got to be careful. One of the options is series diverges. So is the absolute value of r less than 1? So e is like 2.7 squared is like over 4, which is, but yeah, that's true. It converges. And so then the formula we use for geometric series only is a over 1 minus r. A is 1. R is 1 over pi. 1 minus pi over e squared. Probably want to multiply both the top and bottom by e squared. And we could look at the answers. Yeah, none of them are complex fractions, so we're going to want to clean that up. And that is answer D. So, okay. All right, number 2 says, assume that f has derivative of all orders for all real numbers, and they give you the values f of 0 equals 2, f prime of 0 equals negative 1, f double prime of 0 equals 6, f triple prime of 0 equals 12. Which of the following is the third order Taylor polynomial for f at x equals 0? We'll center it at 0. We need all the derivatives of 0. We have it. Third order is going to go up to the third power. We need the third derivative, which we have. So this one's kind of ready to go. Taylor polynomial. You would do this times x to the 0 over 0 factorial. Those are both 1. Minus 1, x to the first over 1 factorial, plus 6, x squared over 2 factorial, plus 12, x cubed over 3 factorial. We could clean this up, and we get 1 minus x plus 3x squared plus 2x cubed. And that matches, the first one's supposed to be 2. That matches answer A. Okay, number 3, multiple choice, which of the following is a Taylor series generated by f of x equals 1 over x at x equals 1. So I think it's not a Maclaurin series, so those memorized versions aren't applicable. So I think we just got to do the work. We got to find a bunch of derivatives. Enough to figure out the pattern because they're all closed form on here, but probably, it's going to be negative x to negative 2, which is negative 1 over x squared. This is going to be positive 2 over x cubed. And that's going to be negative 6 over x to the 4th. So I don't know. Let's try that. Maybe that's enough. It's centered at x equals 1. So we're going to plug 1 into these. Get 1. Get negative 1. Get 2. And get negative 6. So the Taylor series, a lot of times you use capital T for Taylor, is going to be 1 times x to the 0 over 0 factorial minus 1 x to the first over 1 factorial plus 2 x squared over 2 factorial minus 6 x cubed over 3 factorial. Those are going to be ones. So we need to find a pattern. We try and start. I mean, look at all the answers start n equals 0. So let's start n equals 0. Seems like a good reason. And it should keep going. But let's see. So could we write f of x equals 1 over x equals closed form n equals 0 to infinity? So it looks like it's always x to the power of that number factorial. So there's going to be a x to the n over n factorial for sure. Oh, shoot. I forgot something. It's supposed to be minus 1. Dang it. Keep doing that. I looked at the answers and I noticed some of them had that. So I forgot about that. Got to remember. So this should be x minus 1 to the power. So you also look at it has alternating signs. So I think it should for sure have a negative 1 to the n. And these, well, actually, what happens, look at this. These cancel each other out. This number in front cancels it out. So I think we just don't even have that. So I think we're looking for this. And that matches answer E. Okay, number 4, for response, let f be the function determined by the function f of x equals closed form n equals 0, sigma notation, 2x plus 2 over 3 to the nth power. All right, for all values of x for which the series converges. A, find the interval of convergence for the series. Now, is this a geometric series? Yes. If you plug in equals 0, the a value is 2, the r value is all this stuff. And it's a power series because it has x's in the r. But the interval of convergence, that's where does it work, where does it converge, comes from the absolute value of r, has to be less than 1. So we've got to solve that absolute value inequality to find the interval of convergence. So I'd multiply both sides by 3 first, which doesn't affect the absolute values. And this is the absolute value inequality. I like to use this trick. You could do a much more elaborate version from Algebra 2, but this idea from geometry that we used last year in AB Calc AB to solve the absolute value inequality is that it's centered at -2, and we're going 3 away. The absolute values are distance away from 0 normally, but now it's distance away from -2. So that's going to be 1 and -5. It's going to be everything in between. So the interval of convergence is -5 to 1. Okay. All right, page 502. Says exercises 1 through 5 find the polynomial of order 4, fourth order, for the function and use it to approximate the value of the function at x equals 0.2. So number 1, the function is e to the -2x, and it's centered at x equal. All of these are going to be centered at x equals 0, so they're all Maclaurin. And I mean, so we have some options. I'll show you a couple different ways on some of these. I mean, we could say, okay, well, let's build it. Let's find all the derivatives to the fourth derivative. And this is going to be negative 2e to the -2x, and this is going to be positive 4e to the -2x, and this is going to be negative 8e to the -2x, and this is going to be positive 16 e to the -2x. Not too bad. Sometimes it gets really bad. The derivatives are bad, and then we're going to plug 0 into all these. So you get 1 and negative 2 and 4 and negative 8 and 16. So if you'd write the fourth order, it would be P sub 4 equals 1 x to the 0 over 0 factorial, which is all 1, minus 2 x to the first over 1 factorial, plus 4 x squared over 2 factorial, minus 8 x cubed over 3 factorial, which is 6, plus 16 x to the fourth over 4 factorial, which is 24. So we could clean it up. 1 minus 2x plus 2x squared minus 4/3 x cubed plus 2x to the fourth over 3. So that's the fourth order. Now, this is a Maclaurin series, so we could use that memorized version. So have you memorized it? If you haven't memorized it, I guess you shouldn't be using it, but you should be trying. E to the x is 1 plus x to the first over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. So we could use this, and then for e to the negative 2x, plug in a negative 2x everywhere you see an x in parentheses. And look at what you get. So we could do it that way, and you get 1 minus 2x plus 2x squared minus 8 over 6 minus 4/3 x cubed plus 16 over 24 is 2/3 x to the 4. You get the same answer. So you could just write that down and plug in, since it's now they said to use this to approximate the value of the function. So we're going to say, well, f of 0.2 is approximately equal to our fourth order Taylor polynomial of 0.2 plugged into it. And I'm just going to do that on my calculator. So it's going to be 1 minus 2 times 0.2 plus 2 times 0.2 squared minus 4/3 0.2 to the third power plus 2/3 0.2 to the fourth power, and we get, so we get 0.6704. All right. So I mean, maybe I'll keep doing that for some of these. So number 3, let's do 5 sine negative x. So we can say, all right, well, the original function is 5 sine negative x, and the derivative is negative 5 cosine negative x, and the second derivative is positive 5. Well, no, negative, because the derivative of cosine is negative. There's already a negative, so that's positive. And then another negative comes out because of chain rule. Jeez. This is going to be positive 5 cosine negative x. And then the fourth one, which we need for fourth order, it's going to be positive 5 sine negative x. So we plug 0 in, and we get 0. Now, fourth order doesn't mean 4 terms. Fourth order means the last term you have has that power. So that's going to be negative 5 and that's going to be 0. And that's going to be 5. And that's going to be 0. So the fourth order term could be 0. That's fine. That doesn't mean we put the fifth order term just because there was no fourth order term. So P sub 4 would be 0 times x of 0 over 0 factorial minus 5 x to the first over 1 factorial plus 0 x squared over 2 factorial plus 5 x cubed over 3 factorial plus 0 x to the fourth over 4 factorial. So I'm just like plugging everything in and get simplified. That's all going to be 0. Those terms all go out. So for the order Taylor polynomial is negative 5x plus 5/6 x cubed. And that's it. Now, alternatively, we could say, hey, we know that the sign of the x function is, we've memorized it. It's the e of the x function. It's all the odd terms, which starts with x, and then they alternate minus x cubed over 3 factorial plus x to the fifth over 5 factorial, etc. Right? And then if you're going to do 5 sine negative x, then you distribute a 5 to everything, and you plug a negative x in everything. So it's going to be negative 5x minus 5/6 x cubed. Well, actually plus, because the negative gets cubed. It's a negative times a negative. And this one would be minus 5x to the fifth over 5 factorial, and so on. So you could have gotten it that way. I'm just trying to show you both ways. As much as we can, we're going to do this shortcut in the future, but it's really good to know that you can do all of them this way. And you're going to have to do it this way for a lot of them. Okay. The estimation. I'll just do it on my calculator. So it's going to be negative 5 times 0.2 plus 5/6 0.2 to the third power. I'm putting some extra parentheses just to make sure I don't mess up. And we got negative 0.9933. I don't know. I don't know if the book has 4 decimals. So I'm writing 4 decimals for that reason. Quite remember. Okay. So one more of these, number 5. Now this one, I don't know if we can match up easily to one of those on the memorized one. So we might just have to, that's the reason why you might have to do it the long way. So you should feel comfortable doing the long way. Like you should be totally confident. It's tedious and takes a little while, but we need all the functions. So f of x equals 1 minus x to negative 2, which I might rewrite as 1 over 1 minus x squared. And then the first derivative is negative 2. It's going to be positive 2 because the extra negative is going to pop out. Chain rule. So that'd be negative 6, but it's going to be positive 6 because the extra negative pops out. Negative 24, positive 24. Negative 120, positive 120. So then we got to plug 0 into them, including the first one. The first one is the very first one. So that's going to be 1. And that's going to be 2. And that's going to be 6. And that's going to be 24. And that's going to be 120. I don't know if you guys noticed, those are all factorial values, by the way. Right? This is 2 factorial, 3 factorial, 4 factorial. 5 factorial, 1 factorial. Now, the way it works is it's going to be this guy times x is 0 over 0 factorial. And then plus 2 times x to the first over 1 factorial. Plus 6x squared over 2 factorial. Plus 24 x cubed over 3 factorial. Plus 120 x to the fourth over 4 factorial. Now, I could use the factorial knowledge. You know, this is 4 factorial, 5 factorial, 3 factorial, to help simplify it. So we have 1 plus 2x. 3 factorial divided by 2 factorial leaves you with just a 3. Because remember, 3 factorial is 3 times 2 factorial, right? And 4 factorial is 4 times 3 factorial. So the 3 factorials cancel and you just have a 4 left. And so there's your fourth order Taylor polynomial. Okay, so let's see. So I don't know if we could have used a shortcut for that. I mean, can we connect this to one of those memorized ones? I don't think we can, so that's fine. We just did it the old way. So if you want to estimate 0.2, p sub 4, plug 0.2 into that, and just do it on my calculator. So we got 1 plus 2 times 0.2 plus 3 times 0.2 squared plus 4 times 0.2 to the third power plus 5 times 0.2 to the fourth power. And we get 1.56. So it's good practice. Stuff we've been doing a lot of. Okay, let's see. Number 6, directions change for the next 3 problems. So 6 through 10, find the Maclaurin series for the function. Find the Maclaurin series. So trying to find the Maclaurin series, which is just a Taylor series centered at, they either say x equals 0 or they say a equals 0. Okay, so number 6 says sine x minus x plus x squared over 2 factorial. Now, I don't think we want to do all these derivatives. I mean, we could. I mean, I don't know. Let's just try it out, I guess. I mean, this is the original function. I'll try it both ways, okay? It's going to be cosine x minus 1 plus, did I write it down correct? This should be x cubed over 3 factorial is the original one, right? Okay, so cosine x minus 1, multiply the 3 in front, which it just reduces with 3 factorial on the bottom, you get x squared over 2. And then the second derivative, it's not too bad, it's negative sine x plus, multiply the 2 in front, cancels the 2, you have just x. Third derivative is going to be negative cosine x plus 1. They said find the Maclaurin series. So we got to find the whole thing. So we got to find some pattern. And this eventually kind of becomes this really just basic trig thing that never goes away. Right? And then you get negative sine x. And then you get negative cosine x. And it just keeps going like that. So then we could plug 0 into these. Sine 0, 0, 0. That one's 0. 0 in here, that's 1 minus 1 is 0. That one's 0 also. 0 into this, sine 0, 0. That one's 0 too. 0 into this, that's negative. That one's 0 also. And that one's 0. And that one's 1. So then it starts going, and then it's 0, and then it's -1, and then 0. So if all the first terms are just kind of like gone, I mean, you could write it, Taylor series, 0 times x is 0, 0 factorial, plus 0 x to the first over 1 factorial, plus 0 x squared over 2 factorial, plus 0 x cubed over 3 factorial, plus 0 x to the fourth over 4 factorial. And the first one is there. So we might as well not even, write all these other terms. But so I'm gonna say, okay, well, those all go away. And so we have x to the fifth over 5 factorial. And the next one is minus x to the seventh over 7 factorial. And then it's going to be plus x to the ninth over 9 factorial minus x to the 11th over 11 factorial plus dot, dot, dot. So there is a pattern. Let's see if we can figure out what the pattern is. -1. Now, if we start this one as n equals 0, okay, so what is it going to be? How do we get these numbers from these? Is it times double this times 3? Is it time? Okay, maybe we add like 5 to something, right? If we double this and add 5, double. Okay, that's it. Double in add 5. Now for the bottom factorial, you got to put it in parentheses. So here it is. That's the open form. And then the closed form is easy once you've written that nth term, because that's what goes here. Now what I want to try is I want to see if we can try and get it without doing all this work, because these are Maclaurin series and we've memorized some of them. So let's try it the other way. Like, okay, well, the sine x series on its own, we've memorized that, is x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial and on, right? And so if we just say sine x minus x plus x cubed over 3 factorial, we can literally just add these. So we can say, okay, well, let's take this one, that's sine x. If I'm going to use a memorized one, I write it down first. If you can't write it down, then you have no shot. Write it down, make sure you don't mess it up, help you memorize it. Then we're going to subtract x, which is going to cancel those. We're going to add x cubed over 3 factorial, which is going to cancel those. And look what you get. You totally got what we got. And I feel like it was a lot easier. So that option is out there. You would still have to figure out, I think you'd still have to figure out, the pattern and stuff like that. But we figured it out from that. So interesting that we can take different approaches, right? I've done that, I think, on almost every single problem on this assignment. Okay, let's see. Now, most of them. If they're not centered at 0, then okay. Now this one is sine squared of x. Now this one I think would be a little. We would use that, and then you square this, which means you got to distribute all these terms, which you got to distribute an infinite polynomial times another infinite polynomial. I mean, I don't know. I'll try it out afterwards, but seems kind of crazy. Okay, so let's just try it the kind of straightforward way first, just to build it. Now remember, this is the same thing as sine x squared. So you gotta do power rule first, and then you gotta do chain rule, right? And then you're gonna have to do a product rule the next time. So it's gonna be 2 sine x times cosine is gonna be negative sine plus cosine times 2 cosine x. So we could simplify this. It'd be negative 2 sine squared x plus 2 cosine squared x. Okay. Third derivative. It's power rule. It's going to be negative 4 sine, and then chain rule cosine. And this one's going to be 4, but it's going to be negative. Yeah. It's going to be cosine, but then you get a negative sine. I already put the negative there. And then these neatly combine together, it looks like, right? Negative 8 cosine x sine x. So, I mean, I don't know how far we can go with this. This is tough. I mean, it's not terrible, but it's just, things keep shifting around. Like you do another product rule, right? I think we're going to cosine x, and it's going to be plus 8 cosine x sine x. Because derivative of cosine is negative sine. Oh wait, sine. So then you get negative 8 cosine squared. So 8 sine squared. I'll do one more derivative. So next one is going to be a 16, negative 16 cosine, and a negative sine, so it's going to be positive, and the next one is going to be positive 16 sine, and then a cosine, and it simplifies to 32 cosine sine. So, I mean, there seems to be kind of like this back and forth pattern here. Now, we're doing it for 0, so we plug 0 in, and sine 0 is 0. I mean, even though this looks really complicated, it might become like a really simple kind of pattern of numbers that we could write a formula for. So we'll hold out hope. That's going to be 0. That one's going to be 2. That one's going to be 0. That one's going to be negative 8. This one's going to be 0. What's the next one going to be? I guess let's find one more. I just want to confirm this pattern. Okay, so it's going to be another product rule. It's going to be 32 cosine minus 32 sine. Right, so it's going to be 32. So it looks like we're multiplying by 4 each time, and we're missing the middle terms, and we're getting alternating. So if we wrote this Taylor series, 0 times 0 factorial over 0 plus 0 to the times x first over 1 factorial plus 2 x squared over 2 factorial plus 0 x cubed over 3 factorial minus 8 x to the 4th over 4 factorial plus 0 x to the 5th over 5 factorial plus 32 x to the 6th over 6 factorial. So can we see a pattern here? I'm going to keep the factorials. 2x squared over 2 factorial minus 8x to the 4th over 4 factorial plus 32x to the 6th over 6 factorial. So I think the next one would be minus 128x to the 8th over 8 factorial. I mean, that's my guess. And so the nth term, if we start at n equals 0, n equals 1, n equals 2, n equals 3. So there's an alternating part, negative 1 to the n. And then it's going to be x to the 2n plus 2, 2n plus 2. Right? 2 times 0 plus 2 is 2, 2 times 1 is 2 plus 2 is 4, 2 times 2 is 4 plus 2 is 6, 2 times 3. Okay, so that looks good. Over 2n plus 2 factorial. The only thing is we have this number here that's being multiplied by 4 each time. So I think the first term has a 2, and then it's multiplied by a 4 to the power of n. Which we could then use rules of exponents to kind of combine this. So I'm going to write this this term a little cleaner. Okay, so I'm going to say it's 2 to the 2n plus 1. And then we have an x to the 2n plus 2. All over 2n plus 2 factorial. So, oh my gosh. I mean, that looks like the closed form would just be this, right? Negative 1 to the n, 2 to the 2n plus 1, x to the 2n plus 2, all over 2n plus 2 factorial. So that was challenging. I mean, that's a harder one. I mean, still the work we were doing was, finding this pattern was a little hard at the end, but we're just taking lots of derivatives. Just had to be really careful. Now, could we have taken the approach of, well, sine squared is sine times sine? I mean, could we try that and see if, I think it might be able to. So what's sine was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, right? And then you're multiplying it times the same thing. So these are the memorized Maclaurin series. Challenge yourself to memorize these as soon as possible. It's going to make life easier. Okay, and then we got distribute. Now, we could just, this goes on for infinity, but we could just do the first terms and see what we get. So if we do that, we get x squared, right? And then we get minus x to the 4th over 3 factorial. Plus x to the 6th over 5 factorial minus x to the 8th over 7 factorial. And then we do this one and we get minus x to the 4th over 3 factorial plus x to the 6th over 3 factorial times 3 factorial. I don't know. Minus x to the 8th over 3 factorial times 5 factorial plus x to the 10th over 3 factorial 7 factorial. And then you do this one. I mean, I don't know. This is looking pretty bad. So x to the 6th over 5 factorial minus x to the 8th over 5 factorial 3 factorial plus x to the 10th 5 factorial 5 factorial. And so this keeps going now. Does anything clean up? And we're trying to get this same series that we had, which does have an x squared at the beginning, right? And it does have minus 8. Or hold on a second. No. The x fourth term would be next. I have minus 2x to the 4th over 3 factorial, right? Are there any other x to the 4th terms? I don't think so. But that would just give you a 3 on the bottom, which this one, that would be 24. Boom, that gives you the same thing. It does give you the same thing. Now, finding the pattern, I think, is going to be a lot harder because the way it was written up here was a lot nicer. I think with the factorials already here, I'd simplify it and I'd have to try and work backwards to figure out what was going on there, which I don't really have a whole lot of faith. But we are getting the same thing. I don't think it was any easier, and I think it's going to be harder to find the pattern from. So, anyways, I don't think I would do it this time. I don't think that's the way to go. All right, last one, number 10. The function is x squared over 1 minus 2x. All right, so the x squared, we could, just to start making you think, we could do it like this. You know what? I have an idea of how we can do this in a shortcut, which I think is going to be for sure I feel like it's going to be the way to do it here, but I don't know. Because it's going to get, I feel like it's going to get kind of long and messy the regular way. Let's try it the regular way first. So for the regular way, it might be helpful. I don't want to do quotient rule. So I'm going to do it like that. So we got a product rule here. So it's going to be x squared times, it's going to be -1. But a -2 is going to pop out. It's going to be +2. And then this times 2x. And then the second derivative, I mean, this is pretty messy. You have a 2x squared. You have product rule here by itself. So -2 with a -2 is going to be 4. 1 minus 2x to the -3 plus 1 minus 2x to the -2 times 4x. And then you have this product rule. Oh my gosh. I feel like I want to bail on this. Now, let's see if I let's just see. Let's keep going. Now, is there any hope of simplifying these? This is 2x squared over 1 minus 2x squared plus 2x over 1 minus 2x. So the first, if we combine these, do we have any hope? That would be the idea. So you have 2x squared plus 2x minus 4x squared. So you have 2x minus 2x squared. Yeah? Is that better? Doesn't really look like it. Okay, this one, I think we're still working on it. 2x, an extra 2. I mean, so that's the second derivative. Oh my gosh, that looks horrible. That just doesn't look good. I feel like at some point things simplified for me though. So, you know what I think what did I do? I don't know. Okay, so I'm going to take a break from that because I kind of want to give up on it. Alternatively, I would take this approach and I'd say, hey, you know what? This looks like, A over 1 minus R, like the sum. Like this is kind of basic power series stuff. This is your R, this is your A. And then everything's going to get x squared. So f of x equals x squared times, and then this series from this is going to start with 1, and then plus 2x, and plus 4x squared, plus 8x cubed. The general term, if we start at 0, would be, we're going up to the first. So it looks like it's going to be 2x to the nth power, right? So if we just distribute the x into it, the x squared into it, we get x squared plus 2x cubed plus 4x to the fourth plus 8x to the fifth plus dot dot dot, and you have this 2x to the n, and then you have an x squared. Then the closed form, probably want to clean this up. 2 to the n, x to the n plus 2. I don't know if we can do that. But it would be n equals 0 to infinity of 2 to the n x to the n plus 2. Now, this is different than what I have written down in my work. But I'm kind of feeling good about this one. Now, in my work, originally I tried to do it, just do it the long way. And I guess I somehow made some progress in finding some of these derivatives, but I think I don't know. Because up here, f is 0, if you plug 0 in, you get 0. F prime is 0. Plug 0 into this, you get 0. F double prime is 0. And you gotta plug 0 into all that and figure out what that is. And then you gotta find several more derivatives, I think, to establish a pattern. So I think I'm gonna go with what I have written here. Let me just double check it. First term is 1. R is positive 2x. Multiply by 2x each time. Looks good. Distribute the x squared in. Looks good. Looks good. Yeah, so I think I'm going to go with that. So that's sort of a different approach there. I was kind of going back to sort of our most basic power series at the beginning. All right. These are hard. This is the only way you can get better at these, is like really trying to go through a bunch of them and really wrap your head around it. All right.